In this video, I'm going to teach you how to get started on the transformation worksheet. First of all, you need to follow the directions on the first two lines about how to set your calculator up so that the window on your calculator looks exactly the same as what I have on the worksheet. So pause right now and get the calculator set up. Secondly, you need to have a knowledge of what all of these functions look like. You can get out your parent function graphing worksheet and the chart and have some of these graphs handy so that you're familiar with what they look like, because every one of the graphs on this worksheet is a transformation of one of these graphs. So I'm going to just do a quick review of what they are, just so that as you're watching the video you'll know what I'm talking about. So first of all, the first one we have is the absolute value of x. I need to get these handy, so I think I'm going to pause and get them in order. Now, going in order of the functions on the worksheet, this is f of x equals the absolute value of x. F of x equals x squared. F of x equals x cubed. F of x equals the square root of x. F of x equals the cube root of x. F of x equals 2 to the x. F of x equals log base 2 of x. F of x equals 1 over x. And f of x equals 1 over x squared. So the first step when we're looking at writing the transformation of a function is to identify what the function looks like. So if we look at this graph here and we see this characteristic function here, we think, hey, that kind of reminds me of this function, the 1 over x function, because we have a piece that goes like this and a piece that goes like that. So we're thinking of, this is the function that's being transformed, f of x equals 1 over x. Now, what happened to that graph? Well, notice right here that it's centered at 0, 0. So where is the new center of this function? It looks like the new center is right here. It looks like we could have, this could be one of the asymptotes, and this could be the other asymptote instead of the x and y axis. And this is the point 2, 3. So the question is, how do I write a graph that has been shifted over 2 and over 2 and up 3? So to remind you of the transformations, I have a list here of the transformations that we've done. First of all, you could add or subtract something inside the function. In other words, substitute x plus or minus a number for x in the function, and that would give you a horizontal shift left or right. So if we look at that, we're talking about if I changed what was inside the absolute value to, say, x plus 3. Or here if I put x plus 3 the quantity squared with parentheses around it, or x plus 3 the quantity cubed, or the square root of the quantity x plus 3, or the cube root of the quantity x plus 3, or 2 to the x plus 3 power, or the log base 2 of x plus 3, or 1 over x plus 3, or 1 over the quantity x plus 3 squared. That would shift any of these graphs 3 to the left if I put x plus 3 in place of x. So here, if I have 1 over x and I want to shift it to the left or to the right 2, I would subtract 2 from x. So I would say f of x is equal to 1 over the quantity x minus 2. That shifts it to the right 2. Then I want to shift it up 3. Well, shifting it up means you're adding, when we're talking about a vertical change, shifting it up or down, that affects y. We're adding or subtracting outside the function. So in other words, I do whatever the function says, and at the end, then I'm going to add or subtract. So in this case, I do what the function says, 1 divided by x. I've changed the x to shift it to the right. Now at the end, after I'm done with that, at the end I add 3. So this will shift the graph to the right and add 3. And I'm going to pause for a minute and get my calculator open so that I can just demonstrate to you checking your work on this. As you can see, I've typed in the equation down here. I'm going to push enter. And you can see then that this does match what I have on that paper. So by putting your calculator into exactly the same grid as what I have on the paper, you can check to see that it works. Now, another tip I want to show you is if you push delete several times, it'll say, are you sure you want to delete everything? And then you can push yes, and then you can clear your space for the next graph. So you just push delete several times to do that. Okay, back to the other graph. Now we look at our second graph. This looks like an increasing exponential function. So if we go back up to our list, the increasing exponential function that I'm using for the purposes of this worksheet is 2 to the x. So y equals 2 to the x, or f of x equals 2 to the x. Now, one strategy for looking to see what has happened to a function is looking at a key point in the function. Here my key point was where the middle of the graph was. That was actually the easiest thing to see on this. The easiest thing to look at on an exponential function is probably the y-intercept. So I'm going to let x equal 0, and when x equals 0, y is 2 to the 0, or 1. So I have the point 0, 1. So I'm saying normally the graph would go through 0, 1. My new y-intercept is 0, 3. So I've noticed that it's 2 higher than my previous y-intercept, and I'm wondering, does that mean the graph shifted up 2? But I'm going to say no, it probably didn't, because if it shifted up 2, I would expect that now instead of the x-axis being an asymptote, the line y equals 2 would be an asymptote. In other words, I would expect to have had the whole graph move up like this if the whole thing shifted up 2. I'm going to delete that since that's not what happened. So I'm looking now at a stretch. When you multiply a function by a positive number, in other words, outside the function I multiply the whole thing by a number, a positive number, it stretches by that factor. If I were to multiply by a negative number, it would not only stretch, it would also be upside down. It would flip upside down over the x-axis. So I'm looking here at a stretch, and when I'm looking at a stretch, you have to think multiplication. What did I have to multiply by to get 0, 1 to become 0, 3? Well, I would have to multiply by 3. So let's check this out. Now my function would look like this. F of x is equal to 3 times 2 to the x. If I want to check a point, I could put x equals 0 into the function, and I would get f of 0 is equal to 3 times 2 to the 0, which is 3 times 1, which is 3. So the point 0, 3, check. Looks good. I also expect you to graph these and check the graphs on the calculator, whichever. Sometimes it's pretty quick to just check points, but you probably should double check on the calculator as well. Since I know that's the right answer, I'm not going to check that one. Okay, number 3. I see this interesting curve here, and this reminds me of the square root graph. F of x is equal to the square root of x. Now I'm just going to plot that to show you why it reminds me. If I put in 0 for x, I would get 0 for y. If I put in 1 for x, I would get 1 for y. I'm not going to put in 2 for x. I'm going to put a nice number. I'm going to put 4 in for x because the square root of 4 is 2. So I have a graph that looks something like this for f of x equals the square root of x. Now look at my graph that I have here. Not only did it flip upside down, but it appears to have stretched some too, because this looks wider than that does. So another strategy you can use to help you figure out what to do here is to actually label a couple of key points. This is the point 1, 1, and this is the point 4, 2. Then use the same x values and figure out what the y values are on the new graph. So using 1 and 4, I can find the point 1, negative 2, and 4, negative 4. Notice that on both of those points, the y value is twice as big and it's negative. So if I were to multiply y by negative 2, I would get the y from on the old graph to go to the y on the new graph. So it looks like That's what I've done. I've multiplied the function by -2. So f of x is equal to -2 times the square root of x. That will flip the graph upside down across the x-axis, and it stretches so it's 2 times wider than it was before. Instead of here, twice as wide. Instead of here, twice as wide. That's all I'm going to do with you. Notice that you do have functions, some problems that have more than one equation. So when you see some of those graphs that look really complicated, sort of like a design, that's not one complicated equation, that's several simple equations. So look at the pieces of the graph one at a time and figure out the function from that. I've given you exactly how many equations I use to make each graph. And once again, like all the other worksheets, the key is online, so if you get stuck and need some help, I have a worked out key, and I've actually put some tips to kind of show you not just the answers, but sort of my thinking process, how I got those answers. So hopefully that'll get you where you need to go. Good luck and have fun.